Okay, we're going to cover the chapter 26 homework. We're going to start with problem 4, but before I get to the LaTeX file, I'm going to take a look very quickly at example 26.1, and that's the example that I based problem 4 off of. I probably would have had a hard time coming up with a solution, but I looked at the example and saw how they did it, and that's what I used as a basis. And it's a similar problem. I want to get over here to the analysis and how they go about doing it. I'm going to start here at the analyze. The periodic table of the elements in Appendix C shows that the molar mass of copper is 63.5 grams per mole. We call that 1 mole of any substance contains Avogadro's number of atoms. That's 6.02 times 10 to the 23 inverse moles. So they use the molar mass and the density of copper to find the volume of 1 mole of copper. The density is equal to mass divided by the volume. So you solve for the volume, you get mass divided by the density. And from that assumption, from the assumption that each copper atom contributes 1 free electron to the current, find the electron density in copper. And that's what I want to get to. N equals to Avogadro's number divided by the volume. If the volume is equal to molar mass over density, then if you divide by the volume, then it's the density divided by the molar mass, and that's the equation that I use. Now they go on and they come up with one big equation. I just do it in parts, but I encourage you to read over 26.1 so that you can get a good understanding of how I approach the problem 4. And with that, let's do a new share and go to the iPad. Excuse me. Okay, you should be seeing it right now. This is a copper wire has a circular cross section with a radius of 1.25 millimeters. If the wire carries a current of 3.7 amps, find the drift speed of the electrons in this wire. And then there's a part B. I'll read that one once we get to that after we complete part A. So part A, find the drift speed. And I even say I'll follow example 26.1 to solve this problem. First, let's find the electron density of copper. What we know Avogadro's number is 6.02 times 10 to the 26 inverse moles. The density of copper is 8,920 kilograms per cubic meter. And the molar mass of copper is 63.5 grams per mole, which is 0.0635 kilograms per mole. So then let's calculate the electron density, Na over the density of copper. I'm sorry, Na times the density of copper divided by the molar mass of copper. So it's 6.02 times 10 to the 26 inverse moles times 8920 kilograms per cubic meter divided by 0.0635 kilograms per mole. And you end up with, put that all in your calculator, you end up with 8.46 times 10 to the 28 electrons per cubic meter of copper. Now let's calculate the drift speed using the equation 26.4 and solve for the drift velocity. So 26.4 says I average is equals to NQVD times area. So it's the electron density times the charge times the drift velocity times the area. Well, if we solve for the drift velocity, we get I average divided by the electron density times charge divided by area. So we put the numbers in. 3.7 amps is what we're given. 8.46 times 10 to the 28 electrons per cubic meter. That's what we calculated above, times the charge, 1.6 times 10 to the minus 19 coulombs, times the area, which is pi r squared. So it's pi times the 0.00125 meters squared. And you end up with a 5.57 times 10 to the minus 5th meters per second. Now, how do we get the units of meters per second? Well, let me make this bigger. We have amps is coulombs per second, and we have 1 over m cubed times coulombs times square meters. Well, this let me change that to red. The coulombs cancel out. This m squared takes this out and leaves the just 1 over m. So we have 1 over seconds divided by 1 over meters, and both you can invert both of those and it becomes meters per second, and that's what we want. We want the drift speed. Now the second question, the part B, is all other things being equal, what happens to the drift speed in wires made of metal having a larger number of conduction electrons per atom than copper? Well, since there's more atoms available, the speed will decrease. Drift speed when larger numbers of electrons are available. That's what we're looking for. If more electrons are available, the drift speed decreases. In other words, if there's more electrons, then they don't have to go as fast to get the same current. I'm sorry, the same drift speed. Okay, and that's it for number 4. Let's go on to number 12. Now I've got a problem for each of the sections, not counting the section that we skipped, 26.3. Okay, you're working at a company that manufactures electrical wire. Gold is the most ductile of all metals. It can be stretched into incredibly long, thin wires. The company has developed a new technique that will stretch 1 gram of gold into a wire of length 2.4 kilometers. That's 2,400 meters, and uniform diameter. Your supervisor gives you the task of determining the resistance of such a wire at 20 degrees C. Okay, so we go to table 14.1 of the textbook, and we find that gold has a density of 19.3 times 10 to the 3 kilograms per cubic meter. Therefore, 1 gram, 0.001 kilogram of gold has the following volume. The volume is equal to the mass divided by the density, 0.001 kilograms divided by 19.3 times 10 to the 3 kilograms per cubic meter. So the volume is 5.18 times 10 to the minus 8 cubic meters. Therefore, the cross-sectional area must be the volume divided by the length. So area is equal to the 5.18 times 10 to the minus 8 cubic meters divided by the 2.4 kilometers, which is 2,400 meters. And so we get an area of 2.16 times 10 to the minus 11 square meters. So that's the cross-sectional area. Now from table 26.2, I'm sorry, I said 2.6, but it's table 26.2, we see that the resistivity of gold is 2.44 times 10 to the minus 8 ohm meters. Using equation 2610, we can calculate the resistance in ohms. So that's big omega. So R is equal to the resistivity. Now, this isn't density. It's similar, it uses the same rho, but it's a different rho, not density. The resistance is equal to the resistivity times the length divided by area. And that's equal, we just plug in the resistivity, 2.44 times 10 to the minus 8 ohm meters times 2,400 meters divided by 2.16 times 10 to the minus 11 meters squared. So we'll see that the we have m squared here, that cancels out 1m and then the other m. And so all we're left with is ohms, and you end up with 2.71 times 10 to the 6 ohms, 2.71 megohms. Okay, that's the answer. Now I didn't do a problem of 26.3 because I didn't cover that, and I'm not assigning any problems for it. So didn't see the point in assigning a problem or doing an example if we're not going to cover that. Okay, resistance and temperature. Problem 18. A certain light bulb has a tungsten filament with a resistance of 19 ohms when at 20 degrees C and 140 ohms when hot. Assume the resistivity of tungsten varies linearly with temperature even over the large temperature range involved here. Find the temperature of the hot filament. Okay, so we use equation 26.20 to determine the filament temperature, but let's put down what we know first. The initial filament resistance is 19 ohms. The final filament resistance is 140 ohms. The initial filament temperature is 20 degrees, and we're looking for the final temperature. And we know that equation 2620 is the resistance is equal to the initial resistance times 1 plus alpha times delta t, t minus t0. So just the algebraic steps in isolating t, well, we can divide both sides by R0, and R over R0 equals 1 plus alpha times delta t. Subtract 1 from both sides. R over R0 minus 1 is equal to alpha times t minus t0. Then we have R minus R0. I said minus. R divided by R0 minus 1 divided by alpha is equal to delta t. Now we also isolate the t, and we have R divided by R0 minus 1 divided by alpha plus T0, and that's our formula. So using table 26.2, resistivities and temperature coefficients of resistivity for various materials, we see that the temperature coefficient alpha for tungsten is 4.5 times 10 to the minus 3 inverse degrees centigrade. So let's just plug in the numbers. T is equal to 140 ohms divided by 19 ohms minus 1 divided by the temperature coefficient, 4.5 times 10 to the minus 3 inverse degrees Celsius plus 20 degrees Celsius. And we end up with 1435 degrees Celsius, or to 3 significant digits, 1440 degrees C, 1440 degrees C. Okay, and then we have a very simple problem, the potential difference. This is problem 26 from section 26.6. The potential difference across a resting neuron in the human body is about 7.5 millivolts and carries a current of about 0.2 milliamps. How much power does the neuron release? So power is equal to the current times the voltage. So P equals I delta V. You'll have to excuse me, I got a cat on my lap here. So it's 0.0075 volts times 0.002 amps, and that's equal to 1.46 times 10 to the minus 11 watts. Or to put it in engineering notation, you use exponents of multiples of 3. So it would be 14.6 times 10 to the minus 12 watts. So that's 14.6 microwatts. Okay, and that's, Nina, you're in the way. That's it for the examples. I hope this helps. Ow, she just bit me. All right. Not quite.